So, first of all, this could be a very short video. I could just say area of parallelograms is just area equals base times height. And for the most part, that's really all you need to know. What I want to point out is that it's important to keep up with the fact that parallelograms include the subheading of rectangles, which themselves include the subheading of squares. So people often think of these as three separate things to work with when we deal with area problems, but they're really all the same. The major difference is that squares can be kind of narrowed down to a slightly simpler form, and a lot of people will say length times width for rectangles instead of base times height, but that really means the same thing. What I want to note is that most people are comfortable working with rectangles. They'll say, okay, well, yeah, length times width is good enough for me, and they'll find out very quickly that those are all very simple problems to work with. For squares, let's pretend that I can draw a square for just a moment. Let's say that this is a square. For a square, all of your sides are the same length. Of course, we still have our 90-degree angles down here, but all your sides are the same length. So for a square, the area we would say is side squared, because length times width is s times s. So a lot of times they'll say the area of a square is just side squared. That's what you'll see them say a lot. Nothing wrong with that, just want to point it out. But I think for some, the area of parallelogram is a little less clear when we're talking about our more generic parallelogram, where they sort of have these sides that move in this nice diagonal. And they'll say, well, why is it still base times height? Like, there's supposed to be some magical, mystical height that's out here. So that's going to be our height. And this length here is our base. But the idea is, if I wanted to, I could chop off this triangular piece here on the left. And if I wanted to, I could cut this out and I could move it to where this imaginary triangle was here. I could cut this part out entirely and put it here instead. And notice now that I would have from here to here a rectangle with that same base length, because this little piece here would be the same as this little piece here. We would see that this length would be base times height, and we would still just be able to work with the same way we did with this rectangle at the top. As far as actual problems go, these are all very straightforward. I will say that examples for these are pretty narrow. We'll go ahead and just say, for example, we could have a parallelogram that looks like this. They could go in and tell me that the base is, I don't know, 12, and that you have a height over here. They'll often draw it on the outside to make it easier to see. They might say it's a height of 6, and very simply we just say your area is your base times your height. Therefore, in this problem we would have 72 as our area. Now, we didn't give any units here, but if these were in inches, then we would say square inches out here or something of that nature. For squares, keep in mind the reason that they're kind of set aside as their own thing. If I had a square, the major difference is that they might go in and say, well, look, it's a square, so all the sides are the same, all the angles are 90 degrees, and they might just give you a 9. They'll just say, look, one side length is 9, and I have some people come up to me and say, well, I can't do it. I don't know what length times width is. The idea is if one of these sides is 9, all of them are. That's the point of a square. And so we say area is 9 squared, which is just 81. So area of parallelogram, nothing too crazy, but I wanted to have a video up here reviewing that because we'll see some more complicated things in the future that rely on knowing these basic formulas.